Okay, I think we can get started. Good afternoon. My name is Gay Menyee. I'm the Technical Director of the i4 Energy Center. Welcome to everyone to today's i4 Energy Seminar, and also welcome those that are viewing today's seminar on the internet. Today we've seen all the horrific images from Japan of the earthquake and the tsunami, but there's also a third potential disaster, and that is a potential meltdown at the nuclear power plants there. And those reactors are nuclear fission reactors, whereas today's speaker is an expert on nuclear fusion. And nuclear fusion reactors are potentially intrinsically safe. Also does not have any carbon emissions, and the other holy grail, I would say, would be unlimited fuel supply. However, there are a ton of engineering and scientific challenges to design and build a viable commercial nuclear fusion reactor. And today's speaker is Eric Sonnendrucker. He is from the University of Strasbourg in France. He is a professor at the Institute of Advanced Mathematics Research and a National Center for Scientific Research. He is currently working on projects in modeling and numerical simulations of magnetic fusion for ITER. It's a large-scale magnetic confinement fusion experiment being built in the south of France. He also heads the CALVI project in INRIA, the National Institute for Research in Computer Science and Control. So let's welcome Eric today.
Yeah, thank you very much. Thank you very much for giving me the opportunity to speak here. I spent a week here at Lawrence Berkeley, Lawrence Livermore Laboratory. I met lots of very interesting people. The only thing that's not so good this week is the weather, but this is okay. So I'm going to talk a little bit about what we're doing in France about simulation for magnetic fusion. And so the outline of the talk is the following. So first I'm going to recall a little bit, for those who might not be familiar with it, the context of magnetic fusion and ITER. I'll talk a little bit about the modeling, because I'm a mathematician, so I'll show the equations, this I need to. And then I'll talk a little bit about the issues. The biggest problem we have for simulation in magnetic fusion is that we have a huge experimental device, which is ITER, to simulate. And so we need the biggest computer, and even bigger than that, and we need to use them efficiently in order to be able to simulate the physics we want to look at. So I'm going to talk about some issues. Of course, I won't be able to give a full overview, but I chose to focus on two specific problems we are handling in our group at INRIA, which the first one is gyrokinetic Vlasov simulations of the turbulence that happens in the core of the plasma, and the other one are MHD simulations of the tokamak edge. And I'll end with some concluding remarks. So fusion, this is the idea. So the fusion reaction is the one you see here. When you take atoms of deuterium and tritium and you have them fused together, you get a helium particle and a very fast neutron, out of which you can get energy. And this reaction doesn't happen naturally, and you need to confine the particles at a very high density, at a very high temperature. So there's not the risk inherent to fission, where the reaction happens naturally. But it's a lot harder to do, and it's all the harder that when you have charged particles, which you naturally have at these very high temperatures, you have lots of instabilities, and it's quite hard to confine them. There are two basic ways that are pursued to reach these fusion conditions. The first one is magnetic fusion. So this is this picture, where you put your charged particles, very hot charged particles, in order to confine them, you use a magnetic field, because they're charged particles, you can confine them with a magnetic field. And there is an experimental device which is called ITER, which is being built at the moment in the south of France. And this will be operational around 2018, 2019, something like this. Another way to do this is inertial confinement. So this is this picture. There you shoot with laser beams or heavy ion beams at very small targets of deuterium, tritium, and there again you get the conditions for fusion. And there are two experiments based on this which are being built in the world. The first one is very close to here. It's the NIF experiment at Livermore. And the other one is also in France. It's the LMJ laser, which is being built in Bordeaux, which is the southwest of France. So the ITER, so I'm going to focus in the talk on magnetic fusion. And so a cartoon of the ITER project is this. In order to see the size of, to have an idea of the size of the device, here you see a little man. So it's quite big. And this is the tokamak chamber here, where you have the plasma, and you confine it with a very big magnetic field. So this is really a physics experiment, a very big physics experiment that's here to demonstrate that you can really get energy out of fusion. If this experiment is successful, the project is 20 to 30 years after this has started, so this would be around 2050 if everything works well. There will be an experimental power plant, which is called DEMO, which will be built in order to demonstrate that fusion energy can be produced efficiently. And if this works, then maybe everybody will use fusion energy in the future. But it's a long-term project. And before we get there, there's a lot of issues, scientific issues that remain to resolve. And in order to resolve these issues, because the models that I will show later are quite difficult, computer simulation and high-performance computer simulation is an essential tool for understanding what will happen there. So some figures about ITER that you can find on the ITER website. So it's been designed to produce 500 megawatts of output power for 50 megawatts of input power. So this will be the first tokamak that will produce more energy than it's used. The record there are a few tokamaks in the world, and the record for output of fusion power was 16 megawatts, which was produced at the JETS tokamak in the United Kingdom. And so you see there is a huge gap between these 16 megawatts and the 500 megawatts that are intended to be attained in the ITER project. So the ratio of output towards input should be larger than 10, and at the moment it's under 1. And the temperature plasma is will be around over 100 million degrees centigrade. So around 150 degrees. So it's very hot. So France, of course, has a particular relationship to ITER because ITER is being built in France. So apart from investing in making new roads to transport all the pieces of ITER to the site, there is a big research program that started. So first, the history of ITER. So the agreement in order to build this experiment, it's an international convention. It's been signed in 2006, and so that it decided that ITER would be built in Cadarache. And there is also a convention between the European Union and Japan because the last contender for having the tokamak was Japan. So there will be also experimental installation and a very big supercomputing center dedicated to ITER that will be built in Japan with European contribution. And there's so an ambitious scientific program around ITER in the 7th Framework Program of the European Union. And in France, there is a research federation on magnetic confinement fusion, which involves physicists involved in magnetic fusion, experimentalists and theorists, and computational physicists. And there also, so this is, and it involves also a few mathematicians and computer scientists, mainly through INRIA, which is a national research center in France for computer science and applied mathematics. So within this INRIA program, this INRIA large-scale initiative on magnetic fusion, the idea was to involve as many applied mathematicians and computer scientists in France in the ITER project and help the physicists develop better and more efficient codes for ITER simulations. And what we want to, so I am leading this effort at INRIA, and what we want to do is, next to helping really the physicists on the direct implementation and development of numerical methods for the code, also to get a better understanding of the mathematical models and maybe to work on innovative numerical methods that could be even better. But so there are two issues. We want to do more long-time research in mathematics and numerical methods, which might have a more general impact. And next to this, we also want to directly contribute to existing codes that are already run by physicists by improving the efficiency and maybe by improving the computational efficiency and the numerical methods. And we are working mainly on these two codes, Gisela, which is a gyrokinetic code, and JOREC, which is a MHD code. So I'm going to describe this a little bit better later. There's a third code, but which is not as large scale. It's Equinox. This is for the real-time plasma control. This is already used for controlling real tokamaks, so the jet tokamak in real time. So this is a different issue. This is not so much high-performance computing. This is so real-time computing. And these codes really need high-performance computing tools. So now I'm going quickly a little bit over the modeling of plasmas. So I'm going to, won't go too much into detail, but you need to understand a little bit of the modeling to see the issue. So the plasmas, this is what happens when you heat a gas to very large temperatures, then everything ionizes, you have charged particles. The charged particles interact through the electromagnetic fields they create, and then you can model this just by solving the equation of motion in an electromagnetic field. But of course, in a plasma, there are very, very many of these charged particles. So there's no way you could do some simulation based on this model. So this is why you need reduced models. And there is a hierarchy of reduced models. So the first one that is used for some issues, which is a more precise one, is called kinetic models. So these are based on a statistical approach starting from the many particles. So you statistically will characterize a species of particle by a distribution function in phase space. So this tells you basically how many particles you have in a little volume at a given x and velocity. And so this fx dx dv will be the number of particles of the species S you have in this little volume. So the model you get when going to the limit here is what's called the Vlasov equation, and this needs to be coupled to some model that gives you the electric and magnetic fields that the particles generate, and this is generally Maxwell's equations or some reduced model for Maxwell's equations. So the model you get at the end is this one. At the top you see the Vlasov equation, so F is the distribution function of particles, and this is basically a transport equation in phase space, so in the 6-dimensional phase space. And then it's coupled to Maxwell's equation, which gives the electromagnetic field that is generated by the particle. So it's non-linearly interacting. Then, if you go a little bit further in the hierarchy, the next option is what is called fluid models. When the particles collide, you get a thermodynamical equilibrium, and then you can define macroscopic quantity. You can always define macroscopic quantities, but here you can close the relations, and you can find a set of equations on the macroscopic density, velocity of the particles, and temperature or pressure. And then you get this kind of model. So this model looks a little bit more complicated than the Vlasov equation, but it has a big advantage. It's only posed in physical space, only 3D instead of 6D. Of course, computationally, it will be easier to handle. And so the MHD model that I'm going to talk of, MHD stands for magnetohydrodynamics. It's a further approximation of this model, where you can express E in terms of B, and which is very useful in magnetized plasmas like you have in magnetic fusion plasmas. And yeah. So the tokamak. Then once you have the the models, you have the next problem, which is the configuration of this torus where you want to solve the equation. So the first big problem is when you have a very large magnetic field, as you need for magnetic confinement, you have a big anisotropy. The particles are confined across because the Lorentz for the force that the magnetic field exerts on the particles is a transverse force. It's V cross B, it's transverse to the velocity. The force is only confining the particles in the perpendicular direction, but it doesn't do anything in the parallel direction. This means that the particles will go very fast along the magnetic field lines and move slowly across the magnetic field lines. The magnetic field lines is what you see here. They're winding across along concentric tori. And so the trajectories are quite complicated, and you have a big anisotropy of the particles due to this field line. So you need to be very careful when designing your numerical method to do something to handle this properly. So as I said, I will concentrate now on two specific codes we are working on in this large-scale initiative on magnetic fusion in France. So the first one is a 5D gyrokinetic code that simulates turbulence in the plasma code. So the main author of the code is Virginie Grand-Girard at CEA Cadarache. She's working with different physicists at this place. And then we are working in the University of Strasbourg and in the INRIA Calvi team on helping on the mathematical, the numerical issues for this code. And there's another code which is a 3D MHD code for the simulation of specific instabilities that occur in the edge of the plasma, which is called JOREC. And the main author of the code is Guido Huysmans, who was also at Cadarache. Now she joined the ITER project directly. And there are people from INRIA, mainly in the universities of Bordeaux and Nice, who are involved in this project. So I'm going to describe here shortly the physics that is done with these codes. So the first one is the Gisela code, turbulent transport in magnetized plasma. So here you have a picture of the typical simulation results you get when you simulate this. So you can see that there are turbulent structures in the poloidal plane. So in this plane of the tokamak, which look quite noisy. So you have very small scale structures, and it's a lot smoother along the large angle of the torus, along the toroidal region. Okay, so the turbulence has started due to instabilities that occur in the plasma. And here, for this kind of physics, the plasma is not very collisional. So you're very far from fluid state. This is why you really need to use a kinetic model, so 6D phase space kinetic model that can be reduced thanks to the magnetic field. And the other codes, the MHD code, is looking at Helm instabilities. So these are instabilities that occur that starts due to modes localized at the edge of the plasma and are linked to the very steep gradients that you have in the plasma in the operating mode. So the experimentalists found that there is an operation mode where you can confine the energy. The turbulence gets smaller, where you can confine the energy a lot better, which is called the H mode. But the problem with this is that you have a very steep gradient at the edge of the plasma instead of having this one, which is another stable mode. But then this triggers some instabilities that can completely destroy the plasma. So this has been observed in tokamak. So this is a picture of this instability occurring in the jet tokamak in England. So now a few general words on how we should develop the simulation tools. I'm advocating that what you really need is interdisciplinary research. So before, most physicists were working alone on their code and developing a code. So one man, one code, and you did the physics with this. When you're going to such difficult problems as so large-scale simulation of magnetized plasmas maybe doesn't work so much anymore because you can't know everything. So when you know well the physics, maybe you have only a rudimentary knowledge of the numerical methods or of optimization cases. Of course, there are some computational physicists who know this very well and specialize in this, but then, so it's, you can't really know everything. So you have then mathematicians on the other side, so when they work alone, they develop very fancy numerical methods like high-order finite elements with adaptive mesh refinements, and they apply it to academic problems, and they run it not so efficiently. They never solve the real problems, so this doesn't help also. And on the other hand, you have computer scientists who also work on their own. They like to develop very fast and efficient solvers for some specific issues, for example, for linear system solvers. Or in some cases, they want to accelerate simple finite difference codes, but generally they don't work on the real problems either. So when here we have a really challenging application, so magnetic fusion, and we want to develop the efficient methods, the better numerical algorithm, the most efficient, and that also deals with the real physics. And this can be done only if you have specialists of the three fields working together. What's a very important issue for this, that generally when you write your code, you use your simplest algorithm, you don't really think about the real computer you have in front of you, at least when you're doing this as a physicist or a mathematician. And when you look at the typical fusion code performance, they use maybe 5–10% of the peak performance of the better machines we have today, and probably it will be even more difficult when you go to the next generation exascale computers. In order to really use to get everything out of the computers we need to look at these computers and design numerical algorithms specifically for the hardware we have. And still we want to do the real physics. We don't need to forget this. It's always easy to design very fast algorithm adapted to the software that solve academic problems, but we want to solve the real problems also. And so it's when we design the method, we want to ally performance and sophisticated algorithms. So we need to have all this in mind in order to efficiently use the hardware we have. And this is another reason why we really need to have the best people in all the fields to collaborate in order to get what we want out of our new computers. And so all possible optimizations look at whatever exists. And this has to be done not only at the end when you have already the code written, but when you design the code. You have to think about algorithm being able to do this. And these algorithms also should solve the real physics. So this looks difficult, but this is what we should do if we want to use efficiently the machine. It's not just you don't want to scale only to 100,000 processors when using and wasting the processors. We want that the physics we do with 100,000 processors is better than the physics we could do with 1,000 processors. Okay, so now after having said this general word, so I'm going to be more concrete about the codes we are developing in the two applications I was mentioning. The first problem we have is setting up the adequate mesh. So we want to mesh this device here, the tokamak. And one thing that we have is that generally the tokamak is axisymmetric in this big dimension. So the hard thing to mesh is the poloidal plane. And generally what we use is just Fourier transform. We keep periodicity because this generally is efficient, and we want to keep this efficiency in the toroidal dimension, and or we can use a uniform mesh and then use some fast FFT also to do the periodic dimension. This is why we really want to keep periodicity, and we want to mesh essentially the poloidal plane. And some important thing here is still this magnetic field. There are here, these surfaces that you see are called the magnetic flux surfaces, and it's a lot more efficient to have your grid aligned with these magnetic flux surfaces, because you were working close to an equilibrium, and so this gets you better numerical results. So what we are looking at in order to define these meshes that can be aligned as well as possible on the magnetic surfaces are spline curves. I have a mathematical definition of the spline. So splines are regular curves that are designed using a piecewise polynomial that you can make smooth as you want if you go to higher order. And so a spline is just a spline curve is a curve that's defined like this. So you have a linear combination in a given dimension of splines, and it looks like this. So you have this control points. This is the points you see here, and you get smooth curves. You can also, by duplicating some points, you can have also non-smooth pieces if you need them, like you would have at the X point of a tokamak. You can go to any order you want, and then you can use these spline curves to define a mesh of your computational domain. So you have this logical domain where you do the computation. So you have a really structured domain, a structured logical domain that you will use to have efficient computations, and you map this onto onto the physical domain that you are looking at, that you're simulating. So this using NURBS for numerical simulations has been very big in mathematics for the last few years. It's been introduced, the concept, by Hughes, Basilevs, and Cottrell as an alternative to finite element modeling. In finite elements, you used to define a triangular or tetrahedral mesh and associated degrees of freedom on the cells of this mesh. And then this was some hard parts, and you needed to mesh the complicated domains. And isogeometric analysis, the idea is that you define the computational domain using these NURBS curves. That is completely traditional in computer-aided design. So when you have complicated objects to mesh, you can use, you have tools that give you already the decomposition of the boundary of the domain in NURBS. And then you can use this to define your mesh of your computational domain. And you can also use the NURBS as basis functions for your finite element method. And you can improve accuracy by going up in order and increasing the number of degrees of freedom. So this for the typical tokamak. So you have the boundary, and then you just draw this, which is a NURBS curve, and then you just draw these curves to define a mesh of your computational domain. And this will be a logically structured mesh that you can, where you can write finite element methods that work very fast, high-order finite element methods that work very fast. And so these are examples of the meshes that are used in the Jorek code, which is the MHD code. So this is the core of the plasma. This is the closed field lines. There is a point in eta where you have this thing which is called an X point, where inside this point you have closed magnetic field lines, and outside you have open magnetic field lines to allow particles to get out. So we're also working on locally refined unstructured meshes to do the same. So we also mesh this is the full tokamak. So the chamber is this, and we also mesh here the coils of the tokamak, so the full region. And we can extract here the mesh of only the tokamak chamber, and here you have a zoom of this region here. And when we want to simulate the edge region of the plasma, we have this unstructured mesh. So now back to the gyrokinetic model. So this is the gyrokinetic model that is used in GSLR. So as I said, the starting model is the Vlasov-Maxwell equation. So Vlasov equation plus something that models the electromagnetic field. Here, because of the big confining magnetic field, you can reduce the number of dimensions. At the beginning, you have 6 dimensions. Here, you go back to 5 dimensions thanks to this gyrokinetic reduction. And so the numerical solution of this, generally, you have 2 approaches. First, you can simulate the whole magnetic, the whole particle distribution, so which is called full F. Another thing, because we start from an equilibrium, we can just simulate the perturbation from an equilibrium. So this is called the delta F measures, but this is not the full nonlinear. So if you really want to solve the full nonlinear physics, you want to do this. And then for the numerical methods, in the gyrokinetic codes that exist at the moment, you have 2 kinds of methods. Particle methods, where you follow trajectories of particles which represent the distribution function, or you have grid-based methods. So the problem with particle methods is that they're noisy, they have quite slow convergence in 1/square root of n, so it's difficult to get precise results. The problem with grid-based methods is you need a good resolution, so it's giving you very huge problems. You don't have numerical noise, but then there's diffusion. And so for the parallelization, I've already given these slides many times, so it's still debatable whether they're easier to parallelize as particle methods. Some say yes, others say no. Here I have a map of the gyrokinetic codes in the world. And you see there are not so many of them. Most of them are here in the United States. A few of them are in Europe. So there's one in France. This is the one we're working on. This is in Finland. This is in Germany. And this one is in Switzerland. So the requirements for gyrokinetic simulations. So we consider only the ions in our simulations up to now. At the end, we will like to consider as well ions and electrons, but of course the electrons are a lot smaller and have a lot smaller mass than the ions, so they travel a lot faster. So it gives you, it's a lot more difficult to simulate both of them together. We have this 5-dimensional phase space. For the resolution, we need to resolve the trajectory of the particles along the magnetic field lines. This is called the Larmor radius, is the radius of this trajectory. We have a little problem. And yeah, okay. So basically for eta size plasma, the size of our mesh in the poloidal direction, so r and theta here in this plane, needs to be at least 512 cells in order to mesh appropriately eta. So we want to have more than 512 cells. So for a good resolved simulation that was performed last year, we needed this mesh. So 1024 points times 1024. So it's a polar mesh of this. As you see, we had radii and angles. And then in the toroidal direction, physical, we have 128. And we have 128 v parallel velocities and 16 v perpendicular velocities. So altogether, this is a mesh of a lot more than a billion points, and you need to handle this. And you see that the size of the tokamaks, of course, improves the difficulty. This is eta size plasma, this is jet size, and these are 2 other. This is ASDEX upgrade. This is a tokamak that is in Germany. And so for ITER, of course, it's complicated. We need really big meshes. So this simulation, I'm going to show it at the end, has been run in June last year for a whole month on 8,000 processors. Yeah, so we have this massively parallel issue. We have now fusion computers dedicated for fusion, so there is computing power available for these simulations. There is one center in Jülich in Germany that has been open for about more than a year now, and then there's another bigger one that will be built in Japan next year. And already now we have more than 10,000 processors, and I hear that there will be a lot more than that available in the future. The problem is, of course, you need to design the code that can handle efficiently those 10,000 processors. If you have a code that runs that's slower on 10,000 or gives you physics that's not better than on 1,000, you don't need to use these. And so you need to be to look at the constraints on the numerical method. So you don't want to have global transfers when you're having so many processors. You don't want to redistribute globally data. And if you have a sophisticated adaptive method that you want to use, you need to make them competitive. So everything you do that is sophisticated needs to be better than the rudimentary thing that was done before and more efficient. And so the load balance, of course, is more complex. So you really need to look at this very carefully in order that, the code you get at the end is really better than the one you had before. And local methods where you have only static load balancing, of course, are easier. If you want to do something else, you really need to check that it's better than what you have here. So for the parallelization of Gisela, so you need also to have hybrid parallelization, sometimes even more using coprocessors or whatever hardware you have. Here we have up to now MPI OpenMP parallelization, so it scales well up to our 8,000 processors. We have still a weak Poisson solver, which is needed in the code, but this is only a design problem. This we should be able to solve. It's not really, it's not a real problem. So you have the weak scaling. This means that when you double the number of processors, you double also the size of the problem. So this is easier to do than the strong scaling. There you keep a constant size of the problem and you increase the number of processors. So here you see by doing this we have 80% efficiency, and here 92. And if we want to go higher than that, we need to become a lot more efficient and to rework on the code. So this was this big simulation I was talking about before. This is a simulation that was close to ITER size. We had the resolution that we need, more than 512 points in each direction of the poloidal plane. And this was a quarter torus. So normally if we would have wanted to run the full ITER, we would have needed 4 times this. And we ran for 1 millisecond. So the time step is around 10 to the minus 6 seconds. So the mesh is the one I gave you already before, and it ran for 31 days on 8,000 cores. So this is a long simulation. The other problem, of course, you get is you get a lot of outputs. We output sometimes the 5D distribution function and other results. So it's 6.5 terabytes of data that have been stored during this simulation. So then, of course, you need to exploit the data. You don't just want to sit on the disk. So you also need efficient ways to do this. And for those who want more information, there have been 2 talks describing the physics of this test case. Okay, so now a few words on Jorek. So this is based on the reduced MHD equations, where you compute the evolution of density, velocity, temperature, and magnetic field. The space discretization is Fourier series in the toroidal direction, and spline finite elements in the poloidal plane. So we use here Bézier splines, so which are given by this. So here you have a picture of the Bézier spline. There's, as I said at the beginning, for the mesh issue, we have an isoparametric representation of the poloidal plane. So the mesh is computed so that it's very accurately aligned on the equilibrium flux surfaces. The time stepping, so it's a fully implicit solvers. The time steps are not dictated by some numerical criterion and completely independent of the grid size. It's a gear scheme that's used, and we get large systems of equations to be solved at every time step. Where these are sparse matrices, and we use a preconditions GMRS solver, and as a preconditioner, for the precondition, we use the PASTIX linear algebra package, which is developed at INRIA in Bordeaux. And the typical problem has 10 to the 7 unknowns, degrees of freedom. As well, it's parallelized using OpenMP and MPI. So this code up to now runs typically on 256 to 1,500 processors. And of course, we would like it to go up. The Jorek code also has adaptive mesh refinements in it. So this is a refinement of the Bézier elements and using gradients of the current density to as a refinement criterion. So here you can see pictures of a shearing mode instability problem. So these are the refined grid, and this is a picture of the electric potential. So you see, of course, that the grid is refined where you have large gradients occurring. So I'm coming to the conclusions. So as I said, you've noticed there's a huge simulation effort needed to better understand magnetic fusion plasmas for the success of the ITER project. And these rely on very complex code because there's a complex physics, and we want to solve this physics. I want to solve it efficiently on today's and the next generation of computers. ITER is a long-term project. The building has just started. It will run in 2019, so we have still a few years ahead of us to design this efficient code, but we really need to do it. And in order to reach this goal, we really want to have the best computer scientists, mathematicians, and physicists involved. Thank you.
Okay, let's open the floor for questions. Oh, I have 3 questions. First one is, how do you verify that the codes are correctly predicting the physics?
Yeah, so there are some traditional test cases. We know we have some instabilities where we can compute analytically growth rates and things like this. So this is the first thing. On simplified problems, you can have some analytical values that you can use to verify that your code is doing the right thing. And then this can be precise verifications. Then we can also have some numerical validation, so convergence of the code. If we are supposed to have a third order method, we verified that the method is actually third order. This finds a lot of bugs. And then we can also compare to other simulations of other codes.
Okay. My other 2 questions are more general related to the ITER project. You mentioned that the temperature of the plasma is 10 times the surface temperature of the sun. So presumably, is the core of the sun roughly more than 10 times the surface temperature?
And so I got these figures on the ITER website. So I'm not really a specialist of the sunset temperature. I don't know the answer. Maybe somebody else.
Okay, and then when ITER's finally going to go into operation, presumably it's not a commercial reactor, so it's not going to be sustained in operation. So
No.
I guess it'll run in sort of like a burst mode, right?
Yes.
Is it anticipated to run for a millisecond, a nanosecond, or what?
No, it's a few hundred seconds.
That's not bad. So you can actually generate quite a bit of power during
exactly.
that period. Okay.
How do you expect the results of these simulations to affect the actual construction of the reactor? And what if your simulations show it's not going to work?
Yeah, so the construction is mostly decided. What the simulations will help is design experiments on ITER. So when you're going to run when you're going to apply for having experimental time on ITER, you will need to provide simulation results before. So the experiments need to be calibrated with the simulation before they can actually happen. So the simulation tools here are essential for that.
Well, are you getting the physics from previous smaller machines that you're comparing the code with in terms of trying to see that matches the real physics?
Yes, of course, there are comparisons with the experiments from the smaller machines, and that fits reasonably well, yes.
So can you say something about the international collaborations in this general area? Who else is involved around the world? How people here might find out more, or if they're interested and wanted to consider participating, what they might do?
Yes, the collaboration, there are lots of countries involved, so I don't have the United States, of course, Europe, Japan, China, India, I'm missing probably a few others. Korea. Yes, so there are many countries involved in the development, and all of them have some things to do. So, for example, they build pieces for ITER. They help in the research projects, and there are initiatives in Europe and in the United States, in Japan, also very big research projects intended for ITER simulations. And if people are interested in contributing, you probably should contact the persons heading these initiatives locally. So.
Okay, thank you, Eric. Oh, we got one more question. Please, can you?
Thank you. What are the interactions between the mesh refinement and the solver for the MHD code? Is the refinement based only on the physics, or is it specific to the solver?
No, the refinement criterion at the moment is based on the physics. So it's the gradient. Where we have big gradients, it's a very simple mesh refinement strategy. Where the gradients are large, we take smaller cells. Yeah.
Well, thank you very much, Eric. I have a background in mechanical, nuclear engineering, and I'm hopeful that this will be successful and I think it will be, since it's going to go into positive output generation. So eventually, all these problems will be solved. And unfortunately, 50 years from now, I'm not going to be around. But some of our audience will be still here. Okay, thank you very much. By the way, next week is spring break, so there will